This video is a first in a pretty big series covering our Unit 3. Unit 3 is titled Work, Energy, and Power, so we'll talk about work, energy, power, what these things are, and how to calculate them. But first, before we do all that, we have to talk about systems. Right? What is a system? How does this system interact? How do forces affect the system? What energy does the system have, and how can the system do work? Or will work be done on a system? So, learning targets are one, I can identify what a system is. So thinking about a system, it's just something where an interesting interaction is happening. Work could be being done, we could have energy exchanged, we could have a certain amount of energy in our system, but really to define what a system is kind of difficult and also pretty easy at the same time. So the example I gave in class was that I have a bunch of marbles and they're all on the desk, and so I'll draw several marbles, and maybe there's more that you just can't see because they're off screen. But let's say I take one marble and I flick it at another marble. So I take this marble here that I'm putting in bold, and I flick it at a second marble, and the reaction happens, and both marbles go off in this direction. And so no other marbles are hit, and I can draw kind of a box around those two marbles, and I can say that everything inside of that box is my system. And a system is really just the thing that we're observing, the thing that we're calculating, the thing that we're measuring something about. So a system can be it can be a ball, it can be a car, it can be all kinds of things. But there are some important features of a system, and those features are: a system does not have an internal structure. So if we have a car, and inside the car is a bunch of people, and inside of the people is a bunch of food, and inside the food is a bunch of bacteria, we don't care about any of those other things. All we care about is that it's a car, and the car weighs a certain amount, it has a certain velocity, and because of that, it has energy. So there's no internal structure, and we don't really care about all the other forces and stuff going on. We don't care about the chemical energy in the gas tank. We don't care about the friction in the pistons. All we care about is that it's a car and it's moving. And so we can represent a system. Most of our systems can be represented as point masses. So this is just all the masses being compressed into a single point that's very, very small, and it lies right at the center of mass of that object. If I had a block, maybe a mass, and it was uniformly distributed, and I'd say that my center of mass was maybe right here in the middle, and then I could just represent that block as a single dot, and then I could draw maybe some forces, like a normal force, a force of gravity, maybe there's a friction force, maybe there's a pull force, something like that. And I can represent all of my forces on that dot. So a system isn't too complicated for our needs right now. We just need to know that a system is the thing that we're interested in and how to describe that system. When we choose a system, it does have an effect on the analysis that we can do. For example, I said a ball could be our system. So if I throw a ball directly into the air, I could say that there's a couple of systems I can analyze. My ball only, just the ball, could be the system. If that's the case, then we would have to analyze this with something like kinematics. If there was an interaction between the ball and the hand, and maybe, when I throw the ball up, I exert some force on it, and it causes it to accelerate, all that good stuff, I could think of maybe the hand and the ball as being my system. If that were the case, I would have to use forces and Newton's laws to analyze the motion, because there's an interaction where there's forces being exerted on one thing and also back on the ball. The force of the hand on the ball. Also, the ball will exert a force backwards on the hand of the same magnitude. So this is another system that we could define. But if I included also the ball, the hand, and Earth, where there's that gravity force acting between the ball and the earth. What I would have to use to analyze that type of system is energy. And it's not that you can't use energy on the hand and ball or the ball only. It's just that we have to do things a little bit differently. It turns out that if I have the ball and the hand and earth as my system, then that is a conservative system. And so I can use conservation of energy and all that stuff to do. But if I talked about just the hand and the ball, I could talk about work done by the force of gravity. I could talk about the energy, the kinetic energy of the ball that the hand gave it. And I could certainly do an analysis on it using energy, but it's often easier just to use forces in Newton's law for that. And it's also possible to do the ball only as an energy problem. But again, it's usually easier to do kinematics if we have that situation. So that's what a system is. It's just a thing that we can put a box around. It's the stuff that moves. So if something, if you're trying to figure out what system should I select, you should select one that has stuff moving. So the things that move, that should usually be part of your system. However, that's not always the case. Sometimes we're interested in things that don't move. And so if it has like a potential energy somewhere, or if maybe there's a charge separation or something like that, where there's some sort of energy between two objects, those two objects should be a part of your system because it'll allow us to use conservation of energy. But that's really all there is to it. System selection is pretty important for us, and the consequences are pretty big. But if we're careful about our analysis, we can always use energy to solve almost every one of these problems, regardless of what system we choose. It's just a matter of whether we have to use something as work or we have to use something as an energy. So that's all I wanted to talk about for systems, and I'll be back with the next one shortly.